Section: Introduction. In this paper, we introduce a new method for training large language models, which we call in-context pretraining. This method is designed to improve the model's ability to understand and reason about complex contexts that extend beyond the boundaries of a single document. Traditionally, language models are trained to predict the next word in a document based on the words that have come before it. This approach can be quite effective for a wide range of tasks, such as following instructions, engaging in conversation, and understanding written text. However, it can also struggle with more complex tasks, such as reasoning about information spread across multiple documents. Our new method, in-context pretraining, addresses this issue by training the model to predict words based on a sequence of related documents, rather than just a single document. This allows the model to understand and reason about more complex contexts that span multiple documents. For example, if the model is trying to predict the next words in the sentence, for 2022, FIFA set the prize money at 42 meters, it could benefit from knowing that a previous document stated, the World Cup never awarded more than 10 m before 2022. This information could help the model predict a continuation like, the highest so far. In-context pretraining is easy to integrate into existing training pipelines for large language models. It simply involves reordering the training data so that related documents are grouped together. However, this task is not without its challenges. With billions of documents to sort, we need to find a way to group them based on similarity without repeating any data. To tackle this problem, we introduce two new algorithms. The first uses a retrieval model to build a document graph that pairs each document with its nearest neighbors based on semantic similarity. The second algorithm treats document sorting as a traveling salesman problem, developing a solution that maximizes the similarity of documents to their neighbors while ensuring that each document is included only once. We tested in-context pretraining by training language models on a dataset of 300 billion tokens. The results were promising. Across all model scales, in-context pretraining improved language modeling and task performance compared to models trained using the standard approach. We observed improvements in several areas, including in-context learning, reading comprehension, reasoning, and retrieval augmentation. In-context pretraining works by concatenating related documents together during training, rather than random documents. This creates more coherent input sequences, which provide additional learning signals for the model. The process involves two steps: finding related documents at scale, and then constructing input sequences using these related documents. To find related documents at scale, we use a retrieval model to link documents within the training corpus. For each document, the model retrieves the top k most similar documents. The retrieval process uses a model called the contriever model, which maps each document to an embedding by taking the mean pooling of the last hidden representation over the tokens in the document. The similarity between any two documents is then determined using cosine similarity. During the retrieval process, we found that the training corpus contains many near-duplicate documents. To address this, we use the retrieval scores to eliminate near-duplicate documents from the training corpus. We found that this deduplication step is crucial for achieving good performance of language models. Section Summary. In this paper, the authors propose a new pretraining method called in-context pretraining, which improves the language understanding capabilities of large language models, LMs. Instead of randomly concatenating documents during pretraining, in-context pretraining reorders semantically related documents to create coherent inputs, allowing LMs to read and reason about more varied and complex contexts. The authors introduce two approximate algorithms to efficiently sort the documents based on their semantic similarity, and evaluate the effectiveness of in-context pretraining on various language tasks, showing significant improvements compared to standard pretraining methods. Section: Creating Input Contexts, Document Graph Traversal. We're tasked with organizing a collection of documents, denoted as D, which consists of individual documents represented as D_I. Each document has a set of nearest neighbors, denoted as N, D_I. Our objective is to arrange these documents into groups, or inputs, where each group contains related documents. In mathematical terms, we're aiming to create a series of inputs, C_1 through C_m, where each input C_I is a subset of D and contains a list of related documents. Ideally, the documents in each input are nearest neighbors of each other. A simple way to achieve this is to group each document with its top k nearest neighbors, a method known as KNN. This approach ensures document similarity within each group but can lead to data repetition. Some documents may frequently appear as nearest neighbors of other documents, resulting in overlapping documents across different inputs. This repetition can limit the diversity of documents the language models, LMs, are exposed to and may lead to overfitting. To avoid this, we aim to create inputs in such a way that each document appears only once. This can be viewed as a graph traversal problem. We represent each document as a node in a graph and use document similarity as the weight of the edges connecting the nodes. Our goal is to find a path that visits each document once and maximizes the chance that related documents are visited sequentially. This is similar to the maximum traveling salesman problem, which seeks to find the maximum weight path that visits all nodes exactly once. We construct an undirected weighted graph, denoted as G, to represent the documents. In this graph, D represents the set of documents, and an edge exists between two documents if they are nearest neighbors of each other. The weight of each edge corresponds to the document similarity. Finding the exact solution to large traveling salesman problems is computationally intensive, but we can use greedy algorithms to find an efficient approximate solution. We start by selecting a document that hasn't been visited yet and has the minimum degree as the starting node. We then extend the current path by navigating to its unvisited neighboring document with the highest weight. This process continues until we reach a node where all neighboring documents have been visited. In cases where our graph is not complete and only contains edges between documents that are within each other's k nearest neighbors, we extend the graph with an edge of weight 0 to a random unvisited minimum degree document. We start at minimum degree documents because they are most likely to have all their neighbors visited first, and therefore be connected to dissimilar documents in the final path. Finally, we traverse the documents along the path and concatenate them to create fixed-sized inputs suitable for pre-training. In our experiments, we integrate this document ordering method into pre-training pipelines as a pre-processing step during batching. We use the English Common Crawl dataset for pre-training and train models of various sizes using the llama model architecture. To perform the retrieval over our pre-training datasets, we construct a FAISS big batch search, designed for conducting efficient similarity search with large batches of vectors. The total search time is 6 hours, with an average search time per batch of 4,738 seconds. Section Summary. The goal of this section is to create input contexts consisting of related documents by sorting a set of documents and their nearest neighbors. To achieve this, the authors propose a graph traversal approach where each document is included only once. They formulate the problem as the maximum traveling salesman problem, representing documents as nodes in a graph and using document similarity as edge weights. They adopt a greedy algorithm to construct a maximum weight path, starting from documents with the minimum degree. Finally, they concatenate the documents in the path to create fixed-sized inputs for pre-training. Section Baselines. We're comparing our method, which we call in-context pre-training, with two other approaches, the standard method and the k-nearest neighbors, KNN, method. The standard method is a traditional pre-training approach that uses randomly shuffled documents as input. The KNN method, also known as Retrieval Augmented Language Model Pre-training, places each document and its top k most similar documents together in the same input. However, this method can lead to less diversity in the documents the language models, LMs, are exposed to, as documents can be repeated. To ensure a fair comparison, we use the same pre-training data and number of training steps for all three methods. We evaluate these methods on tasks that require understanding of various aspects, including language modeling, in-context learning, reading comprehension, open book question answering, factuality, and reasoning. In terms of language modeling, we measure the perplexity of the three methods on Wikipedia, Archive, and Books Corpora. Our results show that the KNN method does not improve over the standard method, likely due to overfitting. However, our in-context pre-training method outperforms both the standard and KNN methods on all three datasets, suggesting that it provides better pre-training signals and improves the language modeling abilities of LMs. For in-context learning, which involves performing a task without fine-tuning by conditioning on a few demonstration examples, We evaluate our method using 32 demonstration examples across 7 text classification datasets. Our method consistently performs better across all datasets, suggesting that it is more effective at learning from demonstration examples. In the area of reading comprehension, which involves answering questions based on a given paragraph, our method consistently outperforms both the standard and KNN methods across all datasets. This suggests that in-context pre-training improves ELM's ability to understand and reason over the given context. We also evaluate retrieval augmentation, a method that retrieves a set of passages from an external text corpus and prepends it to the input query. We conduct this evaluation on 2 open-domain question-answering datasets, natural questions and trivia QA. In the closed book setting, our method performs comparably or slightly worse than the standard method. However, in the open book setting, our method significantly outperforms the standard method, suggesting that it is more effective in this context. Despite the training objective of KNN being the same as retrieval augmentation, our method still performs better, likely due to the overfitting problem of KNN. Section Summary. In this section, the authors compare their proposed method, in context pretraining, with 2 baselines: the standard method, which randomly shuffles documents in the input, and the KNN method, which places each document and its retrieved top K documents together in the input. They evaluate the performance of in-context pretraining and the baselines on various tasks including language modeling, in-learning, reading comprehension, open book question answering, factuality, and reasoning. The results show that in-context pretraining consistently outperforms the baselines across all tasks, demonstrating its effectiveness in improving language modeling abilities, learning from demonstration examples, and understanding and reasoning over given texts. Section: Datasets and Metrics. We've discovered that language models often produce text that isn't accurate or doesn't adhere to the provided instructions, particularly when these instructions contradict the knowledge the model has learned during its pre-training phase. This is often referred to as parametric knowledge. To assess the ability of language models to follow instructions and handle conflicting knowledge, we use 2 datasets, NQSWAP and MemoTrap. Both of these datasets contain instructions that conflict with the model's parametric knowledge. We used the exact match score as our evaluation metric. Our results showed that the in-context language model, ICLM, performed better than the standard and K-nearest neighbors, KNN, baselines on both datasets. This suggests that pre-training the model in context improves its ability to generate outputs that adhere to prior instructions. The improvements were more significant than those seen in other datasets, likely because NQSWAP and MemoTrap emphasize the challenge of reasoning based on the provided instructions, something that previous language models struggled with. To further evaluate the reasoning abilities of the models, we compared the ICLM with the standard and KNN baselines using the scroll benchmark. This benchmark assesses a language model's ability to synthesize information across texts. We fine-tuned the pre-trained language models, standard, KNN, and in-context pre-training, on the training datasets of the scroll and evaluated them on the test datasets. We used the F1 score for the narrative QA, Casper, and contract Enly datasets and the Rouge 1 score for the QM Sum and Gov report datasets. The results showed that the ICLM outperformed the baselines by about 5%, suggesting that it is better at reasoning. However, we hypothesize that the benefits of the ICLM may diminish to some extent when the models are fine-tuned, which could explain the relatively small improvements in this evaluation compared to our other experiments. Throughout the pre-training process, we closely monitored both the training loss and the downstream task performance for the ICLM and the standard language model. The training loss for the ICLM was consistently lower than that of the standard model. This suggests that the ICLM benefits from having a richer set of relevant prior documents to refer to, while the standard model has limited information to rely on, leading to a higher loss. After training on around 150 billion tokens, the ICLM consistently outperformed the standard model on reading comprehension tasks. This performance gap remained consistent throughout the remainder of the pre-training phase, suggesting that the improvements brought about by in-context pre-training do not diminish with more training. We also analyzed 2 design choices of in-context pre-training, the method for finding retrieved documents and deduplication. We evaluated the models with perplexity on Wikipedia. A key aspect of in-context pre-training is grouping documents by their relevance. We considered 3 levels of relevance: random, clustering, and our document linking method in context pre-training. We found that the perplexity of the language model decreases as the relevance increases. We also compared the perplexity of the models trained with and without the semantic deduplication step. Removing this step led to a significant decrease in perplexity. When near duplicate documents are present in the same context, language models might simply copy from the prior document, leading to training instability. Finally, we evaluated the 7B models trained with the standard method and in-context pre-training, using a varying number of demonstration examples on text classification tasks. The ICLM maintained consistent performance gains over the standard method, even as the number of demonstration examples increased. However, the performance plateaued after 32 examples. Section Summary. The section discusses the evaluation of language models' abilities to follow instructions and generate outputs that are faithful to prior knowledge. The results show that the in-context pretraining model outperforms the standard and KNN baselines on knowledge conflict datasets, highlighting its improved reasoning capabilities. Additionally, an ablation study on the design choices of in-context pretraining reveals that document relevance and semantic deduplication significantly impact the performance of the language model. Section: Pre-training with related documents. We're going to talk about pre-training language models using related documents. Some researchers have tried this on a small scale. They've used documents from sources like Wikipedia that have hyperlinks or citations, and then used these to pre-train a type of language model called a masked language model. Others have used a dataset of news summaries, which was put together by humans, to do the same thing. Some have even used documents from the same date to pre-train language models to summarize articles. But there are some limitations to these methods. For instance, not all domains have hyperlinks, and creating a dataset of news summaries requires a lot of human effort. Also, using documents from the same date limits the range of related documents you can use. So, we're proposing a new method that can gather related documents from the web on a large scale, without needing any metadata like hyperlinks, human curation, or specific dates. This will make it easier to scale up the model for pre-training. Next, let's talk about multitask fine-tuning for in-context and instruction learning. This is a way of improving language models by fine-tuning them on a collection of tasks. Some researchers have done this by combining instructions and training samples from human annotated datasets into single text sequences, and then fine-tuning the language model on these. Others have created their own datasets for each task, using a task-specific retriever to find demonstration examples from the pre-training corpus. This method of multitask fine-tuning can be used alongside in-context pre-training, which is a method that focuses on the pre-training stage. In-context pre-training not only improves the in-context learning abilities of language models, but also their overall language modeling, reading comprehension, and fact-checking capabilities. We're planning to explore the combination of in-context pre-training and multitask fine-tuning in future work. Finally, let's discuss training long-context language models. Some recent studies have looked at fine-tuning language models to extend their length. They've done this by making changes to position encoding and fine-tuning the models on short documents and subsampled documents from pre-training data. But there's a problem with this approach. Sequence documents are quite rare in the pre-training data. For example, less than 5% of documents in a dataset called Common Crawl have more than 2,000 tokens. So, in this work, we're focusing on creating meaningful long context data, which will help language models make better use of their long context window. This sorted data can be used for both pre-training and fine-tuning stages to improve the language model's ability to reason over long contexts.